Today we're going to be talking about our last big family of functions, which is rational functions. So rational functions, we've seen them before, even if we haven't quite named them, because they take the form of something like 1 over x anytime you have the variable inside that denominator of the fraction inside the bottom of the fraction. And we're going to use a lot of our techniques also that we've already covered about how to deal with polynomial functions as well, since oftentimes there are polynomial functions inside of rational functions, and we need to know about how to deal with both of those types of functions. As always, feel free to jump to a particular point in this video, and please note that we're going to, at the end, sort of circle back to two topics that we already discussed before: inverse functions back in section 3.7, and the domain of logarithms back in section 6.3/6.4, because now that we actually have more tools about other types of functions, we can do more interesting things with both of those topics. But first things first, let's just define what a basic rational function looks like. So the most basic type of rational function is just literally 1 over x. So where there's an x inside the denominator, there's just a 1 on top. And he looks exactly like this first graph. So as you might notice, we actually have two sets of asymptotes on this graph. We have one vertical asymptote here at x equals 0, and we have a horizontal asymptote here at y equals 0. And we're going to be doing a lot of work today to discuss why those asymptotes look the way they do, and how we find out where those asymptotes are as well. And similarly, 1 over x squared actually has the same set of asymptotes. We have x equals 0 for a vertical one and y equals 0 for a horizontal one. But the behavior around that asymptote looks different. We sort of have this doubling up behavior whenever we have this x squared associated with that vertical asymptote, while we have this opposite direction behavior when we have just an x associated with that vertical asymptote. And that gets back to this idea of even and odd, even for rational functions as well. So when there's an even power, that behavior looks a little bit different than when there's an odd power. We're not going to go as deep into the difference between even and odd with rational functions as we did with polynomials, but it is still something that's nice to keep in the back of your mind, that the sort of corresponding even part is that we have this almost U-shaped behavior around a given asymptote versus opposite direction behavior around a given asymptote for odd. Now that we've seen what those parent functions look like, though, let's actually do a formal definition. So a rational function is formally defined as where we have a polynomial divided by another polynomial, and the polynomial in the denominator has to be a degree bigger than or equal to 1, which is just to say that, if I just had x divided by 1, that doesn't count as a rational function. That's sort of cheating by making the degree on the bottom 0. So you need to make sure the degree on the bottom is at least 1, so I at least have an x on the bottom. Could be something more interesting like an x to the 100th power or whatever, but at least an x on the bottom, and then I can have whatever degree polynomial I want on that numerator on the top of the fraction. So it could just be a 1, it could be an x plus 2, whatever it might be. And both of these are examples of rational functions, where for this first one there's just a degree 1 polynomial on the denominator, degree 0 on the top since it's just a constant number, while on the other one it's a degree 5 polynomial on the denominator and a degree 3 polynomial on the numerator. We can really, or it could have been flipped the other way around. As we noted before, this is sort of what a basic rational function looks like. So there are no x or y intercepts on the most basic rational function 1 over x because there are asymptotes for both of those. So if you're sort of going to graph a rational function by transformations, not often how we graph rational functions, but if it is something that you could graph by transformations, what you want to know is sort of the two basic points, 1, 1, and negative 1, 1, which you could either just know or you could plug back in that, for example, if I want to plug in f of 1, plug in 1 for x, that becomes 1 over 1, which is just 1. That clarifies that we have the point 1, 1. If I want to plug in negative 1, That becomes 1 over negative 1. 1 divided by negative 1 is negative 1. So then I have the point negative 1 comma negative 1. That gives you 2 points and knowledge of behavior around those 2 points to move this graph around. So you would want to know 2 points and 2 asymptotes. We have our vertical asymptote and our horizontal asymptote, and that would allow you to move around this rational function using transformations if you wanted to. You also could know, again, how the even rational function looks versus an odd rational function, as we touched on earlier. So if it's odd, they're going to be facing opposite directions on both sides of this vertical asymptote, x equals 0. While if it's even around that vertical asymptote, they're going to be facing the same direction. That's the main difference between an even and an odd rational function. So let's just touch on how you would actually look at rational functions using transformations if that was a scenario that made the most sense for that particular situation. So if we have just the basic odd rational function, 1 over x, and we want to shift 2 units to the left and up 3 units, let's look at what that would look like. So for the 2 units to the left, remember left-right shifts go inside the parentheses with the function, so that's going to go inside the denominator. And to go to the left, normally left would be negative, but we always use the opposite sign, so that becomes x plus 2 in our denominator for shifting to the left. And then to go up 3 units, that goes outside the function with the same sign, so that would be the plus 3. So our total transformed function, maybe we'll just call him a new function besides f, I don't know, pick your favorite letter, let's call him g. So g of x would be 1 over x plus 2, and then on the outside a plus 3. And then let's think about how each component is going to move. So we normally have a vertical asymptote at x equals 0, a horizontal asymptote at y equals 0. We normally have the point 1, 1, and the point negative 1, negative 1. And let's look at where each of these is going to move with these transformations. So whenever we're moving left 2, x equals 0 will move to the point, or to the line, x equals negative 2. If we move that same vertical asymptote also up 3, that doesn't do anything because you're talking about an infinitely vertical line going up a little bit more. It doesn't do anything in the grand scheme of things. Similarly, for y equals 0, moving him left 2 doesn't do anything, but then moving him up 3 will move him up to y equals 3. For the point 1, 1, so for the x value being shifted to the left 2, 1 minus 2 gets us negative 1. And for the y value being shifted up 3, 1 plus 3 gets us 4. Similarly, for the point negative 1, negative 1, shifting that left 2, negative 1 minus 2 gets us negative 3. And shifting him up 3, negative 1 plus 3 gets us 2. And then let's just check that this looks like how we expect. So we're expecting a vertical asymptote at x equals negative 2. We expect a horizontal asymptote at y equals 3. And then now I'm going to graph the actual plot in a different color here. So we have negative 1, 4. And then we should have the same general behavior around that, which was sort of a curved line that looks like this in that general quadrant. And then we have the point negative 3, 2, which was a curved line like this in that general quadrant. Now, if you didn't know that that was the directions those were facing, you could have also just picked another point in that general quadrant to see how that would look. So, for example, I could have picked the point 2 and plugged it into the original transform function. So if I plug in 2, for example, that becomes 1 over 2 plus 2 plus 3. So that becomes 1 over 4 plus 3, which is the point 3 and 1/4. So you can already see that 2 should have a point around 2, 3 1/4. So that's why that function generally is shaped to go through those 2 points. And for both asymptotes, it should always be approaching but not touching them. And similarly, in this other corner, you could have, or this other quadrant, you could have confirmed by plugging in, I don't know, negative 5. So if you wanted to find g of negative 5, that would be plugging in 1 over negative 5 plus 2 plus 3. Negative 5 plus 2 gets us negative 3 plus 3. So that's 3 minus 1/3. So if you sort of think on the number line, we're at 3, and then we take away 1/3. So that would leave us at 2 2/3, which is about where negative 5, 2 2/3 would be, about there. So we know that we graphed it correctly. It never hurts to plug in another couple of points to sort of see the general shape of your function. And that's exactly what is drawn here, even more nicely than what we had drawn. The domain of a rational function is something that we've discussed quite a bit before, and we're now just going to be talking about it a little bit more formally. Because just as we noted before, if I asked you to do something like 7 divided by 0, you would answer that does not work. So we're never allowed to divide by 0. Allowed to divide by 0. So on a rational function, you always want to figure out where is my denominator 0, and you have to solve for which x values would make that true, and those are the only things x is not allowed to equal. And that's exactly what these steps are saying. So set the denominator equal to 0, solve for those x values. Your domain is all real numbers except for those. So let's do that in practice here. So here, for example, what am I going to be setting equal to 0? X squared minus 9 cannot equal 0. Now I want to solve for x. In this case, because I have an x squared and no x, it's probably going to be easiest to use the square root property. So I will add 9 to both sides. That undoes each other. We're left with x squared equals 0 plus 9 is just 9. Then we want to undo a square with a square root. And when you do that, don't forget the plus or minus on that square root. So then we're left with x equals, and the square root of 9 is 3. So x is, and remember all the way down where this was, x was not allowed to equal positive or negative 3. So if we think in terms of a number line, that would be an open circle on the negative 3, open circle on the 3. That can be any number smaller than negative 3, any number between negative 3 and 3, and any number bigger than 3. Because the only two numbers I'm not allowed to equal are 3 and negative 3. So that would be negative infinity to negative 3, union negative 3 to 3, union 3 to infinity, when we're thinking about domain there. And parentheses on all of those, since I am not allowed to equal those two numbers. For the next problem, we want to employ a similar technique. So I'm going to challenge you to go ahead and pause this video and try to find the domain of the next function yourself. So for the next function, remember for the domain, I simply cannot divide by 0. 7 divided by 0 is not defined, while 0 divided by 7 is just 0. It's okay if the numerator is 0. We will shortly go over what it means for the numerator to be 0. But here you always want to make sure you're setting up that you want to make sure that denominator is not 0. For this particular case, I'm going to rearrange this so that it looks like how I'm used to. So that'd be negative x squared minus x plus 2. I just flipped around the negative x squared first, the minus x second, and then the positive 2 last. And I don't love having to deal with a negative out front, so I'm just going to go ahead and divide every single term by negative 1. Because negative 1 divided by negative 1 is just 1. And then positive 2 divided by negative 1 is negative 2. And now this looks like something I'm more used to factoring. So I want to ask myself what's going to multiply negative 2 and add to 1. And that would be positive 2 and negative 1. And since the coefficient in front of the x squared is 1, I'm allowed to jump straight to those parentheses. Now I set up my too many equations, so x plus 2 cannot be 0. And x minus 1 cannot be 0. Subtract 2 from both sides, x cannot be negative 2. Add 1 to both sides, x cannot be 1. So again, I want to remind myself on the number line that we've got negative 2 and positive 1, and x is allowed to be any single number in the universe except for those two. So it goes from negative infinity to negative 2, union negative 2 to 1, union 1 to infinity, which is a fancy way of saying x cannot be negative 2 or 1. It can be any other real number except for those. Let's also similarly touch on this idea of rational inequalities. These are going to be solved similarly to those polynomial inequalities, where we're going to want to, in this case, set both the numerator and denominator equal to 0, solve for those numbers, put them on a number line, and then do testing points. Because essentially what we're trying to systematically figure out is if I, for example, have a rational function being bigger than 0, what you want to know is when do I have a positive divided by a positive or a negative divided by a negative. If I have a rational function less than 0, I want to figure out when do I have a positive divided by a negative or a negative divided by a positive. And those changing points of when that will happen will occur whenever the either numerator or denominator is exactly equal to 0, and then that will tell you the behavior on either side of those. So let's look at an example of that. So for example, on this first one, it's already set greater than or equal to 0, so I don't need to rearrange him. And then I want to figure out when does the numerator equal 0, when does the denominator equal 0. So I have x plus 5 equals 0, or negative x plus 1 equals 0. I want to subtract 5 from both sides to undo adding 5 for the first one, so x equals negative 5 would make that numerator 0. I want to subtract 1 from both sides for the second one. Negative x equals negative 1. Then divide by negative 1 on both sides. I also could have added x. That would have worked too in the very first step. So x equals 1. And then these are what I want to put on my number line. Now before I just automatically make the closed versus open circles match the original inequality, I also need to keep the domain of this function in mind. Because domain-wise, what is x never allowed to equal because it would cause me to divide by 0? It can't equal 1 just no matter what. So I have to use an open circle on the 1 regardless. And every single time your denominator equals 0, you have to make sure that that is an open circle on that number line. The negative 5, however, it's okay if I plugged in negative 5 itself. That would be negative 5 plus 5. Over negative 1 times negative 5 plus 1, so that would be 0 divided by stuff, which would be, that stuff would be what, 6? And that's okay. That would just make this thing exactly equal to 0. And that gets a closed circle because I have this or equal to sign on the original inequality. So that is one step that's different from polynomial inequalities, is now you have to think through the open and closed circle, not only based on the inequality symbol, but if domain-wise you're not allowed to plug in that number because it would make that denominator 0, you have to automatically give it an open circle. Now I do my testing points. So I want to pick something to the left of negative 5, and I'm trying to see if the result is greater than or equal to 0. So I'm going to pick, I don't know, negative 6. So I have negative 6 plus 5 over negative 1 times negative 6 plus 1. And again, I'm really just trying to figure out the signs here. So negative 6 plus 5 will be a negative number. Negative 1 times negative 6 makes that a positive 6 plus 1. So that'll be a positive number. And if I have a negative divided by a positive, that result will be negative. If you don't just like thinking through kind of abstractly if it will end up negative or positive, the specific numbers would be that that numerator is negative 1, that denominator is 7, and negative 1/7 is indeed a negative number. So do I shade him in? I do not shade him in because I need a result that's greater than or equal to 0. Then I want to pick something in between negative 5 and 1. Let's say 0, because plugging in 0 is nice when you can. So I have 0 plus 5 over negative 1 times 0 plus 1. Negative 1 times 0 is still just 0, so I just have a 1 there in the denominator, and I just have a 5 in the numerator. 5 over 1 is indeed a positive number, so do I want to shade him in? I do, because I want positive results, because it's a greater than or equal to sign. Then for the last part, I want to pick something to the right of 1. Let's pick something like 2. So I do 2 plus 5 over negative 2 plus 1. 2 plus 5 is 7. Negative 2 plus 1 is negative 1. That is indeed a negative answer. So my final result is just negative 5 with a bracket because I include him to 1 with a parenthesis because I don't include him. For the next one, he's not quite set up the way I want yet because we've just got that negative 2 over there instead of a 0. So I want to rearrange this so that the other side is 0. So I will add 2 to both sides. Negative 2 plus 2 makes 0. I'm left with x plus 9 over x minus 3 plus 2 is less than or equal to 0. Now I have to combine this to be one rational function. So I want to think through, what is their least common denominator? Well, currently the 2 is secretly over 1. The least common denominator between 1 and x minus 3 is just x minus 3. So I want to multiply both the numerator and denominator on the 2 in order to make him over x minus 3 instead. So I will multiply both by x minus 3, which is really just a fancy way of multiplying by 1, right? Because x minus 3 divided by x minus 3 is 1. So then I have x plus 9 over x minus 3 plus, and then I can distribute the 2 times x gets us 2x. 2 times negative 3 gets us minus 6 all over x minus 3. Now that they have the same denominator, I can combine them. So I have x plus 9 plus 2x minus 6 all over x minus 3 is less than or equal to 0. Now I want to combine my like terms. 2x plus x gets us 3x. 9 minus 6 gets us plus 3 all over x minus 3 is less than or equal to 0. I may also note that that numerator does actually factor a little bit, because between 3x and 3 is a greatest common factor. 3x divided by 3 is x. 3 divided by 3 is 1. And I might just rewrite him that way because it's a little bit nicer to see what those testing points are going to be. And this is my inequality written in the way that will actually allow me to solve him more easily. Now I need to put my testing points on the number line. So I want to figure out when my numerator equals 0. So that would be the 3 times x plus 1 equals 0. I could divide both sides by 3 first. X plus 1 equals 0. So x could be negative 1. And then for my denominator equals 0, I want to do x minus 3 equals 0, so x would be 3. Those would be my 2 points that go on the number line. Just because of the way that I have written this out, I'm actually going to put my number line on the top here. So I've got 2 points on that, negative 1 and 3. I want to think through who's going to get an open circle and who's going to get a closed circle. So go ahead and pause your video and ask yourself who gets an open circle, who gets a closed circle. So here, the negative 1 corresponded to solutions in the numerator. So he gets a closed circle because according to this inequality, I'm allowed to equal negative 1, while the 3 gets an open circle because he has to do with the denominator, and that denominator cannot ever actually be 0. Now I want to plug in my testing points. So I want to think of something to the left of negative 1. Let's just say something like negative 2. So if I plug in negative 2, that would be 3 times negative 2 plus 1 over negative 2 minus 3. So that would be 3. That's not a good place to work. So this is normally where I would just go to the whiteboard in class. All right, so let's plug in negative 2 here. So if I plug in negative 2, that's 3 times negative 2 plus 1 over negative 2 minus 3. Negative 2 plus 1 gets us negative 1. Negative 2 minus 3 gets us negative 5. I have a positive times a negative on my numerator, which is a negative, over a negative 5, which is a negative, and a negative divided by a negative is a positive. So my result is positive. And since I want to be less than or equal to 0, according to the actual inequality symbol, I do not want to shade that in. Then you want to pick something in between negative 1 and 3, something like, let's say 0. So that'd be 3 times 0 plus 1 over 0 minus 3. 3 times 0 plus 1 is 3. 0 minus 3 is negative 3. Positive 3 divided by a negative 3 is a negative 1. And negative 1 is indeed less than or equal to 0. So I do want to shade that in. And then you want to pick something beyond 3, something like, I don't know, 4. So then you end up with 3 times 4 plus 1 over 4 minus 3. That's a positive 3 times a positive 5 over a positive 1. So that's a whole bunch of positives divided by a whole bunch of positives. That result will be positive over there. So your final answer is just the numbers that are in between -1 to 3, and you want a parenthesis on the 3 because you don't want to actually include something that's not included in the domain. These would be the most extreme examples because you have quite a bit of rearranging that needs to happen first. And this is where really knowing how to solve those rational inequalities from rational equations from intermediate algebra is going to be helpful. So first things you want to do is rearrange these guys so that the right-hand side is 0. So in particular, I want to subtract over 2 over 9 minus x to both sides here for my first step. So then I have -1 over x minus 6 minus 2 over 9 minus x is less than 0. Then I want to find their least common denominator, which in this case would be x minus 6 times 9 minus x. So in order to make these have the same denominator, the first equation I need to multiply both by what it's missing. So right now they have a x minus 6, so I need to multiply them by a 9 minus x. And for the second equation, it currently has a 9 minus x, so they do not have an x minus 6. Now I can go ahead and start to combine these because they have the same denominator. So in particular here, I'm going to distribute. We've got, for both of these, let's actually distribute the first one first. So on the first equation, I have a -1 times 9. That gets us -9. -1 times x. That gets us positive x. For the second one, we have -2 times x. Gets us -2x. -2 times 6 gets us positive 12. All over, and we have the x minus 6. 9 minus x, still all less than 0. Then we combine like terms in our numerator. So we've got x and -2x combined to make -x. -9 and 12 combined to make positive 3. All over x minus 6, 9 minus x, less than 0. Now we want to actually figure out what are all of our numbers that we're going to put on the number line. So for the numerator to equal 0, we'd have -x plus 3 equals 0. I personally would just add x to both sides to get that 3 is equal to x. So 3 would be one of the numbers on my number line. For the denominator to equal 0, I could have x minus 6 is 0, or 9 minus x is 0. For x minus 6 is 0, you would add 6 to both sides. X is equal to 6. For 9 minus x is 0, I would add x to both sides. 9 is equal to x. So all the numbers on my number line would be 3, 6, and 9. And who would get open circles and who would get closed circles? So this time, it's just a greater, less than symbol anyway, so actually everybody gets open circles. And the 6 and the 9, even further, like double reasons, get open circles because they have to do with our denominator. And now I pick my testing points for each region of the number line. And I'm going to personally use this final form of -x plus 3 over x minus 6, 9 minus x in order to test. So let's say the first point I pick is 0, because that's to the left of 3. So that would be -0 plus 3 over 0 minus 6, 9 minus 0. So that would be 3 over -6 times 9. Negative 6 times 9 is a negative, 3 is a positive, so that is a positive divided by a negative for a negative result. And do I want to shade that in or not according to that symbol? I do want to shade that in because I want my result to be less than 0. Then I want to pick another testing point, something in between 3 and 6. Let's say something like 4. So that'd be negative 4 plus 3 over 4 minus 6, 9 minus 4. Well, negative 4 plus 3 gets us negative 1. 4 minus 6 gets us negative 2. 9 minus 4 gets us 5. Negative 1 divided by a negative 2 becomes a positive. So we have positive 1 over 10. That is a positive. I do not want to shade him in. You may already be noticing this alternating pattern, which is true as long as everything has a multiplicity of 1, which is the case here. But it's still worth double checking that we're going to end up with this alternating pattern like we are maybe conjecturing is happening. Let's plug in something between 6 and 9. Let's say 7. So that'd be negative 7 plus 3 over 7 minus 6, 9 minus 7. Negative 7 plus 3 is negative 4. 7 minus 6 is 1. 9 minus 7 is 2. Negative 4 divided by 2 is indeed a negative. So we do want to shade in between there. And then we want to double check something that is bigger than 9. Let's say 10. So that would be negative 10 plus 3 over 10 minus 6, 9 minus 10. Negative 10 plus 3 is negative 7. 10 minus 6 is 4. 9 minus 10 is negative 1. So we end up with a negative divided by a negative becomes a positive. So as your final result, according to this number line, we have from negative infinity to 3, and then between 6 and 9. And that would be your final result. This next problem also needs to be rearranged as well. So we want to make sure to move everybody to the other side. So we want to set this equal to 0 is the idea. So we're going to subtract x and add 1 here on both sides. So we get 3x plus 4 over x minus 4 minus x plus 1 is less than or equal to 0. Because remember here, these are not like terms because the other ones are being divided by an x minus 4. So we can't do that. We also can't just go ahead and multiply both sides by x minus 4 because you don't know if you're going to end up multiplying by a negative number. So that's going to be no good. Because if we did multiply by a negative, we'd have to flip around that inequality. Actually, here I'm going to give myself a little bit more room to show our next step. Because here we want to give these common denominator now, and that common denominator, the x is currently over 1, the 1 is currently over 1, and the 3x plus 4 is over x minus 4. So x minus 4 is going to be our least common denominator. So I want to multiply both of these by x minus 4. So the first term is going to stay the same. That's just a 3x plus 4 over x minus 4. The second term, I'm going to do negative x times x. That gets us negative x squared. Negative x times 4 is negative x times a negative 4 is going to get us positive 4x all over x minus 4. And for the 1 times x minus 4, that just stays exactly the same. Now I'm ready to start just adding across the top and combining our like terms. So in terms of our x squareds, I just have a negative x squared, so that will just stay as is. In terms of my x's, we've got a 3x, a 4x, and an x. That adds up to 8x. In terms of our constants, I have a positive 4 minus 4. That actually adds up to 0, which is kind of nice. In order to make my life easier in terms of factoring, I may want to go ahead and pull out a greatest common factor there in that numerator, which I believe would be x. So I would have x times negative x plus 8. You also could have pulled out a negative x instead. x minus 4 is less than or equal to 0. Now, in order to find, let me actually write that a little bit neater. Because between x squared and positive 8, their greatest common factor is going to be x or negative x. They'll just flip who gets the negative sign here. And then negative x squared divided by x leaves us with negative x. 8x divided by x leaves us with 8. We still have x minus 4 in our denominator. And now we are ready to put our testing points on the number line. So from the numerator, we'd either have x equals 0 or negative x plus 8 equals 0. For x equals 0, that's already been solved. For negative x plus 8 equals 0, we'd have to add x to both sides. 8 equals x. And for the denominator, x minus 4 is equal to 0. We'd have to add 4 to both sides. X equals 4. Now we're ready to put this on our number line. So we've got 0, we have 4, and we have 8. Here in particular, for the numerator, since this is a less than or equal to sign, we're going to want to put closed circles because it's allowed to equal those numbers. While for, oh, that was the wrong. 4 is not associated with the numerator. Well, for the denominator for x equals 4, that needs an open circle because we're not allowed to equal 4. Here is also where I'm going to, since I showed you sort of the long way of figuring out those signs, I'm going to show you how to use your calculator strategically. Because you can just go ahead and actually put this function into a calculator and then be able to figure out the signs from there. So if I have x times negative x plus 8 all over x minus 4, I've now put that in as a rational function. And then I could put my testing points into my calculator. So for example, something smaller than 0 would be negative 1. And that result is a positive number. And according to my symbol, I only want to include numbers that are less than or equal. So I don't want to include that. If you're going to use it on the calculator here, I would still note somewhere on my paper, okay, I plugged in negative 1 to test stuff to the left of 0. Then you want to plug in something in between 0 and 4. I don't know, like 2. That's a negative 6. And I do want to include negative numbers, so I'm going to shade in between there. Then you want to pick something between 4 and 8. I don't know, something like 6. That's a positive 6. That's a positive number. Since I want less than or equal, I don't want to include that. And then you want to pick something to the right of 8. Something like 9. That's a negative 1.8, so that's a negative number, so I do want to include that. So my final answer, I'm just going to write it above because I'm running out of room down there, is I go from 0, including to 4, open parenthesis, 2, and then 8, including infinity. And all of those are our negative solutions. Now let's talk a little bit more about, now that we know how to algebraically work with rational functions and talk about their domain, let's talk about any vertical asymptotes and removable discontinuities. With removable discontinuities being a fancy way of talking about holes in the graph, so to speak. So a vertical asymptote, as we've touched on before, is the straight up and down vertical line where the graph's approaching but not touching in both directions. So here, that vertical asymptote, for example, would be at x equals 0. In order to identify vertical asymptotes, they're going to always come from restrictions in the domain, but they'll only be the restrictions in the domain that don't cancel out. So in particular, let's say you had something like x plus 4 over x plus 4 times x minus 1. The fact that x plus 4 divided by x plus 4 makes 1 means that x plus 4 equals 0, x equals negative 4. This is your removable discontinuity. aka the hole in the graph, because it was what canceled out. Your vertical asymptote would be what's remaining, this x minus 1, so x minus 1 equals 0, x equals 1. That would be your vertical asymptote. And that's all this kind of says in more words, that whatever's still left after you do your canceling out process is your vertical asymptote. Whatever you canceled out is associated with that removable discontinuity, aka a hole in the graph. And this is another concrete example of this. So here, what would cancel out? X plus 1 divided by x plus 1 makes 0. So x plus 1 equals 0 is associated with x equals negative 1. To find out the y coordinate, you would then plug in negative 1 to what's remaining. So negative 1 minus 1 over negative 1 minus 3 gets us negative 2 over negative 4, so 1/2. So there is a removable discontinuity at the point negative 1 comma 1/2. And that's exactly what you see on the graph here. It's just a literal hole in the graph where it behaves normally all around it, behaves normally to the left, behaves normally to the right, and then I punched a hole in the graph right there at negative 1 comma 1/2, because in the original unsimplified function I can't plug in negative 1, versus x minus 3 is still left. So x minus 3 equals 0, x equals 3. That is your vertical asymptote at x equals 3. If you're talking about domain of this guy, you still care about both. So I still care that x can't be negative 1 and x can't be 3. So you're essentially classifying, okay, both of these guys are issues in domain, but negative 1 is a physical hole in the graph, while 3 is a vertical asymptote. So I go from negative infinity to negative 1, from negative 1 to 3, from 3 to infinity, and that is my full domain, part of it being the vertical asymptote at x equals 3, part of it being the hole in the graph, the removable discontinuity, quote unquote, at x equals negative 1. And that's exactly what this is saying, is removable discontinuity comes at whatever simplifies / cancels out. That's all that's saying in more words. So let's practice differentiating these. So for this first equation, it's almost all factored out for us, but not quite. So the numerator is still x minus 2. For the denominator, we're asking ourselves what multiplies to negative 4 and adds to 0. So that would be x minus 2 times x plus 2. Then I want to ask myself, okay, for domain, I can actually pause and go ahead and do all of that now. Because for domain, x minus 2 cannot be 0, and x plus 2 cannot be 0. So x cannot be positive 2, and x cannot be negative 2. So on my number line, between negative 2 and 2, open circles on both. I can be anybody smaller, anybody in between, anybody bigger. So that's from negative infinity to negative 2, union negative 2 to 2, union 2 to infinity. That's your domain. But now I can actually classify what's what in my domain, because in particular I notice those x minus 2's cancel out, so to speak. X minus 2 divided by x minus 2 makes 1. That would just leave us with 1 over x plus 2 as the quote-unquote simplified function. So that's to say this function behaves like x plus 2 absolutely everywhere except at the point x is equal to 2. So our removable discontinuity, aka a hole, happens at the point 2 comma, and then to figure out the y value, you plug in 2 for x in that simplified function. 1 over 2 plus 2 becomes 1/4. So at the point 2 comma 1/4, I expect a quote-unquote removable discontinuity. And then our vertical asymptote would be whatever's remaining. So in particular, x equals negative 2 is our remaining vertical asymptote. Go ahead and try this next one yourself, and then we will talk about that. So in particular on this next one, first thing you want to do is factor. So x squared minus 25 factors into x minus 5, x plus 5, because negative 5 and 5 add up to 0 but multiply negative 25. For the next part, we want to first factor out an x, and that would leave us with x squared minus 6x plus 5. Then we want to factor that further. We want to ask ourselves what multiplies to positive 5 and adds to negative 6. That would be negative 5 and negative 1. And now we're all ready to talk about domain, removable discontinuities, and vertical asymptotes. Because for domain, we have that x cannot be 0, x minus 5 cannot be 0, x minus 1 cannot be 0. X cannot be 0 is already solved. For the second one, we add 5 to both sides, so x cannot be 5. For the next one, we add 1 to both sides, so x cannot be 1. In terms of the number line, that means an open circle at 0, open circle at 1, open circle at 5, and it can be anything else in between. So there's going to be quite a few parentheses this time because we can be any number smaller than 0, any number between 0 and 1, any number between 1 and 5, and any number bigger than 5. I'm going to shorten removable discontinuity to RD just because it's quite a bit of a handful. So for the removable discontinuities, we want to see what's going to simplify up here. Well, the x minus 5s, x minus 5 divided by x minus 5 makes 1. So I have a removable discontinuity of 5, comma, and then to figure out the y values, you plug in 5 to what's remaining, so that's 5 plus 5 over 5 times 5 minus 1. 5 plus 5 makes 10. 5 times 5 minus 1 becomes 5 times 4, which is 20. And that simplifies to a half. So I have a removable discontinuity at 5, comma, a half, plugging into that simplified function. And the vertical asymptote is whatever is remaining from those issues in the domain that didn't become removable discontinuities. So x equals 5 became a removable discontinuity, and that leaves x equals 0 and x equals 1 as our two vertical asymptotes. And now I've figured out my domain, the removable discontinuities, and the vertical asymptotes of this function. Of course, we noticed that we also had horizontal asymptotes, and we can also have slant asymptotes, quote unquote, which are ones that are more like y equals mx plus b lines as well when we're talking about rational functions. So let's kind of talk about how we find those. So the idea is it's some sort of horizontal or slant line that this function is going to approach but not touch. And that slant line is, again, where it's physically slanted and is in the y equals mx plus b format. So how do you find these? Well, first you want to simplify the function, so if anything cancels out, because you've got the same parenthesis divided by the same parenthesis, you want to simplify that first. Then you want to deal with the remaining numerator and denominator and use polynomial long division. When you do the polynomial long division, if you get y equals a number or y equals mx plus b function, you found the horizontal or slant asymptote, and you just get to completely ignore the remainder when you do that process. So let's look at an example of that. So here, if we're going to find the slant or horizontal asymptote, he's already been factored for us, and he doesn't appear to have anything that cancels out. So I'm going to go ahead and re-expand that denominator. So that becomes 4x plus 2 over x times x is x squared. X times negative 1 is negative x. 5 times x is positive 5x. 5 times negative 1 is minus 5. Combine like terms on that denominator, so that becomes negative x plus 5x is 4x. And now I'm going to set up this polynomial long division. So I have 4x plus 2 divided by x squared plus 4x minus 5, so whatever is on top, so it's always like inside the kind of division house, divided by the outside of that division house. So that'd be like, okay, x squared times what gets us 4x, and I've already run into an issue because I'm not going to be dealing with a polynomial anymore. In particular, if I do 4x divided by x squared, That's going to be 4 over x. I don't tend to put like the over x in there. That's no longer a polynomial. So this is just 0 with a remainder of the entire thing. I can ignore the remainder. So that's my literal answer. Y equals 0 is the horizontal asymptote. It's going to be horizontal if you just have y equals a number. It's going to be slant if it ends up being a y equals mx plus b situation. Let's try this next one. So for this next one, I first want to ask myself if I'm able to factor this. So I want to see what's going to multiply to positive 3 and add to negative 2, and that's actually just not going to work. Nothing multiplies to a positive 3 and adds to negative 2, so it can't be factored. So I can go ahead and just jump to setting up our polynomial long division. So I have 3x squared minus 2x plus 1 divided by x minus 1. I want to ask myself x times what gets us 3x squared, so I do 3x squared divided by x. That leaves me with 3x. Then I want to do 3x times x minus 1. 3x times x is 3x squared. 3x times negative 1 is minus 3x. And then I want to subtract that entire thing. So that would be minus 3x squared plus 3x. 3x squared minus 3x squared makes 0. Negative 2x plus 3x makes x. Drop down the plus 1, and then I want to ask myself x times what gets me x plus 1. And I actually can ignore the remainder, so I can actually stop there. This is my asymptote, so y equals 3x plus 1 is the slant asymptote, because I got a y equals mx plus b equation. Let's see about this next one. So our numerator doesn't factor. Our denominator, I want to ask myself what multiplies to negative 5 and adds to 4. That would be x plus 5 and x minus 1. And then nothing appears to cancel here, so I'm good. I can just go ahead and set it up based on the original. So I have 3x squared plus 2 divided by x squared plus 4x minus 5. I want to ask myself x squared times what gets us 3x squared, so I do 3x squared divided by x squared. That leaves us with 3. And I actually could technically just stop here, because I'm allowed to ignore the remainder. I've already gotten to the ones place, so to speak. I've already gotten to the constant, so I'm good. That just is my asymptote. So y equals 3 is the horizontal asymptote. Now let's look at this one. So here I've got on the bottom that factors out to x minus 1, x plus 1. That doesn't simplify at all with my numerator, so I'm just going to go ahead and set up my polynomial long division. I've got 5 times x to the 5th divided by x squared minus 1. I would say x squared times what gives us 5x to the 5th, so I do 5x to the 5th divided by x squared. That gets me 5x cubed. And then I technically could keep on going, but this is already a larger power than y equals mx plus b. So I know this will be neither. There is no slant or horizontal asymptote. There will actually be like some really funky sort of asymptote, but it's not one that we care about in this class. So as soon as you get a power that's bigger than x, you can just stop and be like, there's none. Now I want to have you pause the video and ask yourself if you noticed any patterns to what type of asymptotes we just came up with, in particular to how the power on the numerator compares to the power on the denominator. Because that's actually going to tell you a lot of information. In particular, let's say we said that the numerator was some coefficient within x to the n power some coefficient with an x to the m power, maybe plus some other stuff on there, but really paying attention to that leading term. If n is less than m, something in particular happens. If n is equal to m, something in particular happens. And if n is greater than m, something in particular happens. Also, I should probably throw in some examples here. So if n is, let's say, something along the lines of, I don't know, x over x squared plus 1, n is less than m if they're exactly equal, such as 2x squared plus 3 over x squared minus 2. We'll maybe make that a 3x squared minus 2. If we have it where n is exactly 1 more than m, so something like 2x squared plus 3 over x, for example, or if n is more than m plus 1, so something like 3x cubed plus 3 over x. Different particular things happen in each case. And again, I encourage you, pause the video and see if you can figure out what happens in each case. So in the first case, we will, no matter what, have a horizontal asymptote at just y equals 0. Because if you start trying to do that long division, you will quickly say, oh, x squared doesn't go into x, 0. For the second one, you will have a horizontal asymptote at y equals the ratio of those leading coefficients. So in particular here, if you had something like 2x squared plus 3 divided by 3x squared minus 2, you would ask yourself, what would I multiply 3 by to get 2x squared? So you would really be doing 2x squared divided by 3x squared, which would just get you 2/3. For the next one, that's when you have a slant asymptote, and then you have to get the y equals mx plus b using long division. There's no way to just do it more quickly than that. And the last one will always turn out to be none. And that's exactly what this is saying here. So in particular, this is just sort of repeating exactly what we just said. So if n is equal to m, horizontal at y equals 0, or if n is less than m. If n is equal to m, then that will just be a horizontal at y equals the ratio of those leading coefficients. If n is equal to m plus 1 exactly, then you have to do long division for a slant asymptote. And if n is bigger than just n plus 1, then there is none. So I sort of remember that as the first case would be something small over large. We have the same over same. We have plus 1, the denominator plus 1 over the denominator versus something huge over small. However you want to think of it. And you can always just actually break out the long division to confirm exactly where. Unlike a vertical asymptote, it is possible to cross a horizontal or a slant asymptote. So you never cross a vertical asymptote because that's a domain issue. However, it is possible to cross a horizontal or slant asymptote. And to do that, sorry about that. To do that, you just literally find out, plug in, so for example, if you got y is equal to 0, you plug in 0 is equal to the function and solve. So whatever is that asymptote, you just set it equal to the function. Solve for y, or solve for x. If solving for x works, great, you figure out where it crossed. If it doesn't work, it doesn't cross. So let's look at this as an example. So first of all, you may want to just factor this to make sure nothing simplifies. So in particular, on the numerator, we might notice that there is a greatest common factor of 2x. Apologies if this was a little bit of an abrupt transition, but I realized that I had made a small error where I had just forgotten that there was an extra x floating around when I initially did this problem. So we're going to go back and do this problem again. And if you're thinking, this is the first time I've seen you do this problem, Never fear, that's why I edited it out. So for this problem, the first thing you do want to do is still factor the numerator and factor the denominator. So on the numerator, we want to think what is their greatest common factor. That would be a 2x. And then we want to think about what's left in parentheses, in particular 6x cubed divided by 2x would leave us with a 3x squared, and negative 10x divided by 2x leaves us with minus 5. And 2x cubed and 5x squared, their greatest common factor is x squared. First time around I did this, I put an x instead of an x squared. Would have been the type of thing that whenever you go back and double check your work, you would see. And then we have 2x cubed divided by x squared leaves us with 2x. 5x squared divided by x squared leaves us with plus 5. Now here we can notice what simplifies is x divided by x squared leaves us with just an x down there. And then I do want to go ahead and distribute this back in to set up my long division. So we got 2 times 3x squared is 6x squared. 2 times negative 5 gives us minus 10. X times 2x gets us 2x squared. And x times 5 gets us 5x. Now in order to find our horizontal or slant asymptote, we could notice the shortcut that it should just be at 6 divided by 2 is 3. Or we could formally set up the long division of 6x squared minus 10 divided by 2x squared plus 5x. We ask ourselves 2x times what will give us 6x squared, so we can do that division off to the side, and that will give us 3. And then we know we're allowed to ignore the remainder, so we know that a horizontal asymptote at y equals 3 is what we're going to roll with. Now we can plug in 3 for y in our simplified function in order to solve for x. So our first step that we'll want to do is on that denominator, we'll want to multiply that denominator to both sides. That makes 1, and then we can distribute the 3 in. 3 times 2x squared is 6x squared. 3 times 5x gets us plus 15x. 6x squared minus 10. Now when we subtract 6x squared from both sides, that is super nice. We're just left with 5x equals negative 10. And then as a final step, we'll divide both sides by 15. We'll notice both the top and the bottom divide by 5. That leaves us with negative 2/3. So we know this occurs at negative 2/3 for x because we just solved for x, comma 3 for y because we solved it by solving for 3 for y. So that is the point in which this function crosses its horizontal asymptote. This one would be a similar idea. First, I might want to see if he factors. There's nothing that's going to multiply to 1 and add to negative 4 on top, for example, so he doesn't. In this case, I have to do the polynomial long division because it's going to be an instance of a slant asymptote, and I need to know where it is. So I first ask myself x times what gets me x squared, so I can do x squared divided by x. That leaves me with x. Squared divided by x. That leaves me with x. Now I want to multiply x by x plus 2. That gets us x squared plus 2x. And then I want to subtract the whole thing, so that becomes minus x squared minus 2x. X squared minus x squared makes 0. That's negative 6x plus 1. Then I ask myself, x times what gets us negative 6x? Negative 6x divided by x is negative 6. And then I can actually just stop because I'm allowed to ignore the remainder. So I have a slant asymptote at y equals x minus 6. Now to figure out where it crosses, if it does, I can still just plug this in for y. So I have x minus 6 is equal to x squared minus 4x plus 1 over x plus 2. I want to, again, get rid of that denominator, so I will multiply both sides by x plus 2. That makes 1. I want to FOIL this out, so I get x times x is x squared, x times negative 6 is negative 6x. 2 times x is plus 2x. 2 times negative 6 is minus 12. Drop down the other numerator. Combine like terms, negative 6x plus 2x is negative 4x. Then I would want to move all my x's to one side. And then something in particular happens because x squared minus x squared, it makes 0. Negative 4x plus 4x also makes 0. So I'm left with negative 12 is equal to 1, which again means it never crosses because I got a solution that doesn't make sense. So let's talk about intercepts. So x-intercepts will end up simplifying to where the numerator is equal to 0, but let's sort of pause and think about why. So if I had something like x plus 3 over x plus 4 is equal to y. To find an x-intercept, that means you want to plug in y is equal to 0. So I plug in 0 is equal to x minus 3 over x plus 4. You would start to simplify by multiplying by x plus 4 on both sides. That makes 1, so you're left with x minus 3 equals, and 0 times anything, including x plus 4, is just 0. So you really are just going to end up at the end of the day solving for when the numerator is equal to 0. For the y-intercept, that's actually really nice because you just plug in x equals 0, and if x equals 0 is not allowed to be plugged in because of the domain, then there is no y-intercept. So let's practice this because here it's already pre-simplified, which is super nice. So for the x-intercepts, let's just say you forgot, and being that the numerator is equal to 0, I would just go ahead and naively plug in y is equal to 0. Place f of x with 0. We have x minus 2 times x plus 3 all over x minus 1, x plus 2, x minus 5. I would start solving by multiplying both sides by that entire denominator. That makes 1, and what's 0 times anything? Still just 0. And I'm right back to that numerator. Now I set up my two mini equations, so either x minus 2 is 0 or x plus 3 is 0. Add 2, subtract 3. So x could be 2, or x could be negative 3. So it's at 2, 0, and negative 3, 0 are our two x-intercepts. For the y-intercept, you want to plug in x is equal to 0. So you find f of 0, so that would be 0 minus 2, 0 plus 3, over 0 minus 1, 0 plus 2, 0 minus 5. So that's negative 2 times 3, over negative 1 times 2 times negative 5. Negative 2 times 3 is negative 6. Negative 1 times 2 is negative 2 times a negative 5 is positive 10. You can divide both the top and the bottom by 2 for negative 3/5. So 0, negative 3/5 is your y-intercept. Go ahead and pause your video and see if you can go ahead and find all the intercepts of this one. Hopefully you noticed that x plus 1 divided by x plus 1 makes 1, and that I don't want to include those because those are issues in the domain. In particular, x cannot equal negative 1 ever. For the x-intercepts, you should notice that plugging in y is 0 ends up being that once I multiply over x times x minus 5 to both sides, that just goes away, and you're just left with that numerator anyways. So I set x minus 3 equal to 0, x plus 2 equal to 0, add 3 to both sides to get rid of subtracting 3, x equals 3. Subtract 2 to both sides to get rid of adding 2. We end up with x equals negative 2. So I have an x-intercept at 3, 0, and negative 2, 0. For the y-intercepts, that's when I want to plug in 0 for x, and it will actually end up working out for the y-intercepts if you do that in the simplified or unsimplified version, because once I get 0 plus 1 divided by 0 plus 1, that just ends up making 1 anyway. But it's probably a good habit to still do that in the simplified function. Ooh, and then what problem do I run into? I end up with negative 3 times 2 over 0 times negative 5. So now I'm trying to divide by 0, so there's none. So now let's talk about how we put all this information together to make the graph of a rational function. And a lot of times, for the sake of everybody's sanity, you'll be asked to work backwards more often on an exam where you're given the graph and you have to write the function. But in order to understand how that looks and works, you still have to sometimes sketch the graph and go forwards as well. So in order to sketch the graph, you basically have to find all of the information we just found. So you got to find the y-intercept, you got to find out who's a removable discontinuity, who's a vertical asymptote, you have to find the x-intercepts, and then you have to try to plot and see how the function overall looks. So let's take a look at an example here. So first thing I like to find out is my y-intercept, if it exists, because it's actually usually the least amount of work. So I plug in 0 for x, I get 0 plus 2 times 0 minus 3 over 0 plus 1 squared times 0 minus 2, 2 times negative 3 over 1 squared times negative 2. 2 times negative 3 is negative 6. 1 squared is 1 times negative 2 is negative 2, 3. So I have a y-intercept at 0, 3. I'm going to go ahead and plot him. Now I want to find my x-intercepts. So for the x-intercept, that would be 0 plus 2 times 0 minus 3. Whoa. I was just on automatic pilot finding my y-intercept again. That is not correct. For the x-intercept, you plug in 0 for y. When you end up multiplying over the denominator to both sides, it ends up going away, and I'm just left with that numerator. Moving ahead of myself there. I want to solve for x for the x-intercept by plugging in 0 for y. So I get the x plus 2 could be 0, or x minus 3 could be 0. Subtract 2 to get rid of adding 2, so x could be negative 2. Add 3, so x could be positive 3. So I have two x-intercepts at negative 2, 0, and 3, 0. Now I want to figure out my asymptotes and removable discontinuities. Nothing cancels out, so I have no removable discontinuities. For my vertical asymptotes, that'll happen whenever those denominators are 0. So I have x plus 1 is 0, x minus 2 is 0, so x equals negative 1. And if you notice, he is even, so it should be facing the same direction in both directions when we're talking about around him. So an even one will either be that they're both facing up around the asymptote, or be that they are both facing down around the asymptote. So that's something to keep in mind. That's not actually an aspect that we test you on as often, but it's something that's good to keep in the back of your mind. Undo subtracting 2 by adding 2. And this is an odd asymptote, so it will either be the case that in one direction going up and in the other one going down, or that direction going up and that direction going down. So somehow opposite directions. So let's go ahead and sketch them. So we have an even asymptote here, and we have an odd asymptote here. Now we want to figure out horizontal or slant asymptotes. In particular, even we could literally expand it out, but we should hopefully notice that the highest power on top is an x squared. And on the bottom, since I have a squared times a first, on the bottom will be an x cubed. And when the numerator is smaller than the denominator, what type of asymptote does that become? That becomes a horizontal asymptote at y equals 0. And I've in particular actually already figured out exactly where he crosses him by finding those x-intercepts already. Otherwise, I would formally solve for it. So there's actually already quite a bit of information I know from that. So in particular, I know because he never crosses that horizontal asymptote here in the middle, because I didn't get any x-intercepts there, I know that this middle part has to have a behavior that looks like this. Otherwise, he would have to dip down and cross the x-axis down here for that y equals 0 asymptote. I also could have plugged in a few numbers around there to really confirm that behavior, but I already know he should look like that for that reason. Similarly, because I know that this first asymptote is even, I already know he needs to be approaching but not touching around that even asymptote there, because I know that he has to be facing the same direction around the even asymptote there. Had I not known that, I would have wanted to plug in a number or two to kind of figure out his overall behavior. In particular, probably plug in something in between -2 and -1 to figure out that it should be going up around there, and maybe plug in something around -5, -4, -3 to find out that they're going down around there. And then similarly, because the other asymptote is odd, I have to know that he's facing opposite directions around there. So if he's facing up in this center part, he's got to be facing down in this other part. Or again, you could have plugged in like 4 or 5 or something in between 2 and 3 to sort of confirm that behavior. And that was some extra room in case you needed it. To write a rational function from the graph the other way around is something that you may be asked to do a little bit more often, because it's often a somewhat faster process, since you don't have to find every single piece of components every single time. It's sort of given to you in a way. So let's practice identifying those key pieces. So you hopefully noticed right away that there appears to be 2 vertical asymptotes. And then which one's considered odd and which one's considered even? This one is odd because he's facing opposite directions around him, while this one is even because they're facing the same directions around him. So there's one here at x equals -1, and there's another one here at x equals 2. So let's start to think through my function. So where in my function will those vertical asymptotes appear? Will they be in the numerator or denominator? They will be in the denominator, and for x equals -1, what will that be specifically in parentheses? It'll be opposite signs, so x plus 1, so that eventually you solve backwards of x plus 1 is equal to 0, subtract 1, x is equal to -1. And the other one would be x minus 2, and then you would square him because he is an even asymptote. Next things we want to identify would be those x-intercepts. So we have an x-intercept at -2, 0, and another one at 3, 0. So if we want to think about where that appears in our function, that would be a parenthesis up here at x plus 2, and it appears to have just goes through the graph there, so we're not talking about any sort of even multiplicity or anything. And then we also have for the 3, that would be x minus 3, and again he goes through there, so that would be again just an odd multiplicity, not even. And then just like before, we still say there's an unknown part. We could have some sort of unknown multiplication factor, because I could stretch this, stretch or compress this any way that I wanted by multiplying just a number out front, and that would maintain those same asymptotes and same x-intercepts. We also might have noticed what appears to be a horizontal asymptote at y equals 0. And here, since my numerator does indeed have a highest power of x squared and my denominator has a highest power of x cubed, I'm good. That would result in a horizontal asymptote of y equals 0. What's a key point I could use to solve for that stretch factor? That would be this point down here of 0, -2 would be a good one, although you could also pick any other points that appear evenly on the graph. So I plug in -2 for y, and at that point 0 is x. And now I can solve for that stretch factor. So I'm going to simplify those parentheses first. 0 plus 2 is 2. 0 minus 3 is -3. 0 plus 1 is 1. 0 minus 2 is -2. All squared will get us 4. So I have -2 is equal to 2 times -3 is -6. 1 times -2 squared. -2 squared is 4 times 1 is 4. Now I want to undo dividing by 4 by multiplying by 4 on both sides. So -8 is equal to -6 times a. Get rid of multiplying by -6 by dividing by -6. -8 over 6 simplifies to +8 over 6, which then further simplifies by dividing by 2 to 4 over 3. So I can now plug that back into the original to get my final answer is 4 times x plus 2, x minus 3, over 3 times x plus 1, x minus 2 squared. That would be my final answer with that stretch factor. So now that we are more comfortable with working with rational functions, let's revisit inverses and let's revisit the domain of logs, because both of these are things that we can now ask some more interesting questions about on something like a final exam now that we know how to work with rational functions a little further. So in particular, for inverses, recall the first sort of optional step is that you plug in y for f of x. Then the first real step that you absolutely have to do is switch x and y. And then your goal will be to solve for y. So what do we want to do first? Well, we want to get this rational function part by itself, so I might undo the adding 4 by subtracting 4 on both sides. Then I get x minus 4 is equal to 2 times y minus 3. Then I want to undo having a y down here in the denominator, so I might multiply both sides by y minus 3, keeping in mind when I do that I'm going to have to use parentheses. And as tempting as it might be to distribute this out, I would actually encourage you not to, because since that x minus 4 doesn't have a y in it, I would just divide both sides by x minus 4. That makes 1. So I'm left with y minus 3 is equal to 2 divided by x minus 4. Then I would add 3 to both sides, and that is now my beautiful inverse function. And now we can talk about the domain and range of both the original and this new inverse. So we have f of x, we have the inverse of f of x, and let's talk about the domain and range of both. And here, just for the sake of space, I'm going to use non-interval notation, but you could always, it's good practice to translate this to interval notation. So in the original, what is f of x not allowed to equal? X cannot equal 3. So what does that mean about the inverse? For his range, y cannot equal 3. Now for the inverse function, what's his domain? X cannot equal 4, so that means for the range, y cannot equal 4. And this actually can help you with graphing and figuring out components of this as well, because it should be the case that for this function, however it ends up turning out, is that it's going to be that the y value is never going to be 4. So there might be some sort of asymptote there or something like that, which you would figure out further by you would want to combine this rational function by either, well, actually, let's pause. We could think about this before I say that. You could even think about this in a transformational way, right? Because we've added this 4 on the outside, he's shifted up 4. So that has moved that horizontal asymptote up 4. You also similarly, if you combine this to make one function, by multiplying that 4 by x minus 3 divided by x minus 3 to be determined to combine it to one rational function, you should similarly find a horizontal asymptote at 4 that this guy never crosses. So this is kind of another way to think about where those horizontal asymptotes are and whether or not they cross them. Let's go ahead and find the inverse function of this next guy. So normally, as sort of an optional first step, you would plug in that f of x is the same thing as y. And then as your real first step, you have to replace all the y's with x's and all the x's with y's. And then your goal is to solve for y. So I would still say you would first want to get rid of that denominator. And now this time I would actually distribute. So that would be xy minus 2x is equal to y plus 3. Now I would move all y's to one side and all terms without a y to another. So in particular, I would add 2x over to the other side and subtract y to this side. And you're really just rearranging. So I get xy minus y is equal to 2x plus 3. Then, since both xy and y have a y in it, we could factor out a y. And what would be left? Well, xy divided by y leaves us with x. Negative y divided by y leaves us with negative 1. And then as my last step to get y by itself, I can divide by x minus 1. So then I just found out that y is equal to 2x plus 3 over x minus 1, and that is my beautiful inverse function for the other guy. 2x plus 3 over x minus 1. And now I can think about both the domain and range of both the original and the inverse here. So on the original, the domain is x cannot be 2. So that is the range on the inverse, that y cannot be 2. On the inverse, the domain is that x cannot be 1. So the range on the original is y cannot be 1, which if you notice is what we would have predicted the horizontal asymptote is at, because x to the first divided by x to the first. The horizontal asymptote is going to be y equals the ratio of its coefficients, y equals 1. And then we just confirmed by finding the inverse that this guy never actually crosses that. So the range is actually that y never equals 1. So let's practice some of these inverse functions a little bit more with rational functions. I'm going to actually encourage you to pause your video and try both of these on your own before we go through them together. So recall, as our first real step, we have to replace f of x with y. Or first real step will be replacing x and y flip-flopping. As a first optional step, replace f of x with y just to orient yourself. Then as the first non-optional step, you switch all y's with x's. Switch all x's with y's. And then your goal is to solve for y. So in particular here, I would multiply both sides by y minus 3. So I get x times y minus 3 is equal to 2y. And then my goal is to solve for y, so I want to move all terms with a y to one side without a y to another. So I'm going to go ahead and distribute that x. So that would be xy minus 3x is equal to 2y. Again, I want to move everything with a y to one side, everything without a y to another. There's a couple different ways you could do this, but I might notice that there's already just a y on the right and no something without a y on the left, so I might just subtract over xy to both sides. And then I would notice that both 2y and xy have a y in it, so I can factor out a y. 2y divided by y leaves us with 2. Negative xy divided by y leaves us with negative x. And then as a last step, I would want to divide by 2 minus x. So my final inverse function would be negative 3x over 2 minus x. So you might have equivalently divided every term by a negative and flipped it the other way around. That would be 3x over x minus 2. Those are equivalent statements if you just think about pulling out a negative from every term. Either way, I can still think of the domain and range of both the original and the inverse function. So for the original function, the domain is x cannot be 3. So that means his range is that y cannot be 3. Which if you sort of look at the inverse, regardless if you think of it as negative 3 divided by negative 1 or 3 divided by 1, you predict that there's going to be a horizontal asymptote there at y equals 3, and that it looks like, according to our math here, that's never going to cross that. For the domain of the inverse, regardless if you think of x minus 2 can't be 0 or 2 minus x can't be 0, either way you get x cannot be 2. So the range for the original is y cannot be 2, which might have been what you predicted by where his horizontal asymptote is. If it's at y equals 2 over 1, we just found out by finding the inverse that he's never going to cross that. For this next one, again, your first optional step is just replacing f of x with y. And then your first required step is that you switch y and x, so I get x is equal to y plus 1 over 2y. Then you want to get rid of having a y in the denominator, so you multiply both sides by 2y. So we get 2yx is equal to y plus 1. Then you have to move every term with a y to the same side, so I subtract y on both sides. I get 2yx minus y is equal to 1. Now both of these terms have a y in common, so I can pull out a y. 2yx divided by y leaves us with 2x. Negative y divided by y leaves us with minus 1. And then I can divide both sides by 2x minus 1. So our inverse function is equal to 1 over 2x minus 1. And now I can think about the domain and the range of both the original and the inverse function. So on the original function, the domain is that x cannot be 0. So the range on the inverse has to be that y cannot be 0. And if you notice on the inverse, it does have a horizontal asymptote at y equals 0. And then we just confirmed by solving for this that it will never cross it. So in particular, it actually has no x-intercepts, because if you try to set that numerator equal to 0, 1 equals 0 makes no sense. And on the inverse, x cannot equal, you might have to do a little bit more solving this time. So you add 1 to both sides, divide by 2, so x cannot equal a half. So the range on the original is y cannot equal a half, which if you notice, because x has a secret coefficient of 1, we do indeed have a horizontal asymptote at y equals a half on the original there. The last thing that we want to kind of revisit now that we've gone over some spicier inequalities is the domain of a logarithm, because now I can put more interesting things inside of a logarithm and still solve for its domain. Because remember, since a logarithm is an inverse exponent and the range on the exponent is 0 to infinity, for a log, the domain of a regular log is 0 to infinity, and then to solve for the domain of a slightly spicier log, you have to set whatever's inside the parentheses. In this first case, x squared minus 9 has to be bigger than 0. Or in the second case, that would be x minus 3 over x plus 2 has to be bigger than 0. And that's really the only kind of new step I'm able to do here now, is before I only put something linear inside those logs and had you find the domain, and now you're able to find with pretty much any sort of interesting function inside the log and find the domain. I'm going to encourage you to pause the video and go ahead and solve both of these inequalities and then compare with what we get. So for the first one, that factors into x minus 3 times x plus 3, because we're asking ourselves what multiplies to negative 9 and adds to 0. Then I go ahead and put the solutions to both on a number line. So to the side, setting either x minus 3 is equal to 0, add 3 to both sides, x equals 3, or x plus 3 is equal to 0, subtract 3 from both sides, x is equal to negative 3. Then I pick testing points in each of these regions. So for the first region, we could have something like negative 4. So that would be negative 4 minus 3 times negative 4 plus 3. So that would be a negative times a negative, which equals a positive. So those numbers do work. If I want to pick something in between, let's say 0, that would be 0 minus 3 times 0 plus 3. That is a negative times a positive. That is a negative. So it does not work. If I want to pick something beyond 3, something like positive 4, that would be 4 minus 3 times 4 plus 3. That is a positive times a positive. So that does indeed work. So I would end up with negative infinity to negative 3. Union 3 to infinity would be our domain. Same idea if we have a rational inequality. We want to set for where the numerator is equal to 0. So in this case, add 3 to both sides, x equals 3. Want to set when the denominator is equal to 0, subtract 2 from both sides, x is equal to negative 2. And then since this is a strictly greater than, I go ahead and put open circles on both anyway. And then for the negative 2 in particular, that's also an issue in domain in the rational function as well. So it definitely cannot equal negative 2. And it can't equal 3 itself because this is, again, a strictly greater than sign. And then I just pick testing regions in each part. So let's say beyond negative 2 would be something like negative 4. Negative 4 minus 3 is negative 7. Negative 4 plus 2 is negative 2. A negative divided by a negative is a positive. So I do want to shade him in. Something in between negative 2 and 3 might be 0. So 0 minus 3 0 plus 2, that's a negative divided by a positive is a negative. We don't want to shade them in. Something beyond 3 would be something like 4, so 4 minus 3 over 4 plus 2. That is a positive divided by a positive. We are good. We do want to shade them in. So our final domain would be negative infinity to negative 2, union 3 to infinity. As always, feel free to check your textbook if you want to see even more examples, and do be sure to reach out to your professor as well.